Hey there. Today we're going to talk about something we feel every single second of our lives. But do we really get it? So let's just dive right in. What exactly is gravity?
When you think of gravity, what comes to mind? Probably an apple falling from a tree, right? Or just the thing that keeps our feet on the ground. But is that really the whole story? Is it just the simple downward pull? Well, it turns out the reality is way bigger than that.
So let's zoom out a bit. We've got to think bigger. Gravity isn't just about down. It's about this mutual attraction that connects everything in the universe.
Okay, so here's the key thing to get. Gravity is a fundamental force of attraction. And check out these words, any two objects. It's not just the Earth pulling on you. Now, it also says it applies to things with mass or energy. We're going to focus on mass for now, but you'll want to stick around because that energy part, that's where things get really wild.
And I mean, gravity is literally everywhere. Of course, it's what's keeping you from floating off into space. It's the reason planets are doing their beautiful dance around the sun. It's even what pulls giant clouds of gas together to light up new stars. But here's a fun one. It also means you're being gravitationally pulled by the very chair you might be sitting in right now. Wild, right? And this just shows you the mind-blowing scale of it all. This isn't just a local thing. Right this very second, yes, you, are being pulled on by the supermassive black hole at the center of the Andromeda galaxy. That's over 2.5 million light years away. And guess what? It's being pulled on by you too. Now sure, the force is so tiny you'd never feel it, but it's there. It's real. Now, this all might sound super complicated, right? A force connecting everything? But believe it or not, way back in the 17th century, one guy figured out that this whole cosmic dance follows two surprisingly simple rules. And these are the two golden rules of gravity, all thanks to Isaac Newton. It really just boils down to two things. How much stuff there is, that's mass, and how far away that stuff is. That's it. Let's break them down.
Okay, rule number one, mass matters. It's pretty simple. The more massive something is, the more gravitational muscle it has. I mean, just look at our solar system. The sun makes up over 99% of all the mass in the whole system. That's why its gravitational pull is so powerful it can keep every single planet, from tiny Mercury to giant Jupiter, locked in orbit.
And rule number two is just as easy to grasp. Distance matters. Gravity gets weaker the farther you go. So the more you separate two objects, the less they feel each other's pull. But it gets weaker in a really specific, kind of interesting way.
So, here's what's so cool about how it weakens. It's not like you double the distance and the force gets cut in half. Nope. If we could somehow just poof, double the distance between the Earth and the Moon, the gravity between them would drop to just 1/4 of what it was. So yeah, distance is a huge deal. And we see a perfect example of this every single day. The moon's gravity is pulling on you right now, but it's so far away that you don't feel a thing. It's completely unnoticeable. But the oceans? That exact same pull is strong enough to literally lift trillions of gallons of water, creating the high and low tides all across the globe. Pretty incredible.
Okay, so we've got it down, right? Gravity is all about mass. Simple. But what if I told you that's not the full story? This is where our understanding of gravity takes a seriously weird turn.
So that brings up a really tricky question, one that seems to break our own rules. If gravity is all about mass, what happens to something that has no mass at all? Should gravity even notice it's there? And the answer, amazingly, is yes. Gravity can, and it absolutely does, bend the path of light. This is one of the most mind-bending discoveries in all of physics, and it totally changes the game. You see, light is made up of these tiny little particles called photons. And here's the kicker. Photons have energy, for sure, but they have zero, zilch, no mass. And yet, when a beam of light from a faraway star zips past a massive object like our sun, its path gets bent by the sun's gravity. And that's the proof. Gravity doesn't just pull on mass, it pulls on energy too. So, let's recap. Gravity is this universal force of attraction, pulling on both mass and energy, and it follows those two simple rules of mass and distance. But that leaves us with one last massive question. We know how gravity works, but we still haven't talked about why. What is it about mass that actually creates this force? Why does it warp the universe around it? Why are things pulled together across the vast emptiness of space? Well, answering that question, that takes us on a whole new journey, from Newton to Einstein and into the very fabric of space-time itself.